Hey guys, so in today's lesson, we are once again going to be going over some review of Science 10 chemistry stuff. So this is all stuff that you should already be familiar with. We're going to be going over how to draw Lewis dot diagrams, also called structural diagrams or stereochemical diagrams for ionic compounds. So Lewis dot diagrams are stuff that we have gone over in Science 10. We briefly touched on electronegativity then as well, but we didn't go as in depth into that. So for this, you do need to know how to draw the Lewis dot diagrams of both atoms and ionic compounds. You also need to know how the bonding of ionic compounds and other compounds in general is affected by electronegativity. You should also know the pattern of electronegativity on the periodic table. Then we're going to go over different types of intramolecular forces and then finish off with going over the properties of ionic compounds. So when it comes to bonding, all atoms have valence electrons, which are the electrons in the outermost orbit. Most atoms also obey the octet rule that says that the first shell can hold up to 2 electrons, all the rest can hold up to 8, and an atom is most stable when its outermost orbital is full, so when it has the full set of valence electrons. Atoms then bond by trying to fill their outermost energy levels and become stable. This is true for both ionic and covalent bonding, though they work in different ways to try and fulfill that. So Lewis dot diagrams represent only the valence electrons of an atom. The electrons can exist in 4 different places, the top, bottom, and both sides. The electrons can pair up, but won't until all of the other spaces are filled. They would prefer to be alone. Electrons that do end up paired are called paired electrons. The other electrons are called lone electrons. Only unpaired electrons can be involved in the bonding process with both ionic and covalent molecules. We'll talk more about covalently bonded molecules later and also some of the exceptions to that rule. But in ionic compound, it's going to be the lone electron that gets lost from the metals, and then it will go over and bond with another lone electron on the non-metal. That is how we then create a positive ion and a negative ion, is by that loss and gain of electrons, and then those oppositely charged ions bond with one another. Oh, okay, so I'm going to switch over to my document cam now to show you how we actually represent this. Okay, so the first example we're going to go over is magnesium chloride. We know that this is ionic because it is a metal bonded to a non-metal. And I would recommend when you're doing this for an ionic compound, or that you start by writing out the formula for the ionic compound if you're just given the name like this. So the formula for this would be Mg for magnesium, Cl for chlorine. Then we write the charges of each. So magnesium has a charge of +2, chlorine has a charge of -1, and then we cross our charges. From that, we get MgCl2. You don't have to show this whole process. You can just jump right to the formula. That's also fine. But the reason why it's handy to have the formula written out is that it tells us that when we draw this, we're going to need 1 magnesium and 2 chlorines. So I'm then going to draw out my magnesium. Magnesium is in the second row of the periodic table, meaning that it has 2 valence electrons. So 1, 2. Draw them on opposite sides, so you could draw them here and here instead if you would like. And then for my chlorine, it is in the 17th column of the periodic table, meaning that it has 7 valence electrons. So 1, 2, 3, 4, 5, 6, 7. And I am going to need 2 of those, so I'll draw one on the other side of the magnesium as well. Obviously, it's going to look the same. Okay, then I need to show the movement of my valence electrons from the metal, in this case the magnesium, to the non-metals. These lone electrons around the magnesium can only go where there is a lone electron on the chlorine. They cannot go to an already paired set of electrons. So 1 is going to go to each lone electron on the chlorine. And then my last step is to write this out using some square brackets. So I'm going to have my magnesium and each of my chlorines in some square brackets. I then need to write out the valence electrons that now exist around each of those atoms. So my magnesium won't have any, they both left. My chlorines will each have 8 now because they've each gained a new electron. So I will just draw 8 electrons around each of my chlorines. If you have done your electron transfer properly, your metals should always have no electrons. Your non-metals should have a full outer orbital. So in this case, 8. And then the last step is to write in the charges of these ions. Magnesium, being in the second column, is going to have a charge of +2. Chlorine, because it's in the 17th column, is going to have a charge of -1. And then that would be your final answer. So in order to get full marks, you would have to show me everything that I have drawn out here. It is also important to note that you can only have metals touching non-metals. You cannot have 2 metals touching one another. You cannot have 2 non-metals touching one another. So if you had written this out the same way, only you had taken this chlorine and put it over here instead, that would be incorrect. You cannot have your chlorine drawn over there. It has to be touching the metal. It cannot be touching another non-metal. Okay, so I could have drawn this chlorine down here at the bottom instead, underneath the magnesium. That would also have been fine, but it has to be touching the magnesium. It cannot be touching the other chlorine. Okay, I'm going to give you guys an example to try now. So I would like you guys to try to draw nitrogen. Oh, I wrote that wrong already. Lithium nitride. Okay. Pause here and then come back to the answer. Okay, so this is the answer that you should have gotten. Lithium has a charge of +1, which would cross over. Nitrogen has a charge of -3 that would cross over. So lithium nitride is Li3N. So I need 1 nitrogen and 3 lithium. Lithium being in the first column, each has just 1 valence electron. Nitrogen being in the 15th column is going to have 5 valence electrons that you must draw like so. And then each of these lone electrons is going to bond with one of the lithium's electrons. That leaves me with a structure that looks like this. So my nitrogen is going to have a charge of -3. Again, just because of the column of the periodic table that it's in, you can know that. And it's going to have all 8 valence electrons now. Each lithium is going to have a charge of +1, again, because it's in the first column. And then don't forget your square brackets. It does need to look like this, but you certainly could move one of these lithiums to the top instead if you round it. Electronegativity refers to the ability of an atom to attract a valence electron. So as you can see in those diagrams that we just did, our metals are losing electrons, so they don't have a very strong ability to attract electrons, whereas our non-metals are gaining valence electrons, so they do have a stronger ability to attract valence electrons. So generally speaking, non-metals are going to have a higher electronegativity than metals. With that being said, you can also compare different non-metals to each other or different metals to one another. The more extreme the electronegativity of an atom is, the more reactive it is. So atoms with really high electronegativities are really reactive, and atoms with very low electronegativities are very reactive. The highest electronegativity on the periodic table belongs to fluorine, so it is the most reactive of the nonmetals. The lowest electronegativity belongs to either cesium or francium, but both are around 0.7. There is debate on which one actually is the lowest, but those are both very, very reactive metals. And the general trend of electronegativity, if you look on the periodic table, is, actually, I'm going to switch back over to my document. Okay, so on the periodic table, the general trend is that electronegativity is lowest down in this corner here where cesium and francium are. And then as you move up and diagonally across the periodic table towards fluorine, that's going to be how you increase electronegativity. So as a general rule, we say that the closer an atom is to fluorine, the higher its electronegativity is. Now, if you're doing a worksheet or something like that, and you're comparing, say, like sulfur and oxygen, or oxygen and chlorine, to see which one has the highest electronegativity, you can just look that up. There are charts of electronegativities. On a test or quiz, you won't be given a chart like that. You will just have to know this general rule, but you won't be asked to compare things that are the same distance away from fluorine. So you might be asked to compare like oxygen and bromine, for instance, but not oxygen and chlorine. Okay, when it comes to bonding, the more different the electronegativity of the atoms are, the more likely it is to form an ionic bond. That's why metals with nonmetals form ionic bonds, because metals have really low electronegativities. That's what allows them to lose electrons and become positive. Non-metals have really high electronegativities. It's why they gain electrons and become negative. So metals, low electronegativity, lose electrons. Non-metals, high electronegativity, gain electrons when you have that ionic bond form. That is the electron transfer that causes cations and anions to form, and then those oppositely charged ions form the ionic bond. The ionic compounds then arrange themselves into a 3D crystal lattice structure. So you do need to know that name, by the way. Ionic compounds always form crystal lattice structures, which is just the way that if you say have a positive ion, every single side of that positive ion, top, bottom, side, front, back, every single side of that positive ion will be surrounded by a negative ion. And then every negative ion will be surrounded like that by positive ions. The compound, even though it's then made of ions, will have a net charge of 0 because all the positive and negative ions end up canceling each other out. If the electronegativity of both atoms are high, that is when you get a covalent bond forming. That's generally between two nonmetals. And we'll talk more about covalent bonds in another lesson. Okay, intramolecular forces are a type of force between atoms within a molecule. This is different from intermolecular forces, which are between different molecules. Intramolecular forces are very, very strong. They include both ionic and covalent bonds. Both of those types of bonds are intramolecular because they are inside molecules. So in an ionic compound, the intramolecular force is an ionic bond, and it is just that force of attraction between the cation and the anion. So just to kind of illustrate what I'm talking about here, and we'll get into this more in a later lesson. But if you have like an NaCl molecule, so this would be an ionic bond right here. That would be the ionic bond between the positive and the negative cation. That is an intramolecular force, specifically an ionic bond. You could also have something like water. A water molecule looks like this, H2O. These bonds here and here are covalent bonds. They're also intramolecular. In this case, just covalent instead. But this is a molecule, this ionic bond is inside of the molecule, so it is intramolecular. This whole thing is a molecule. These bonds are inside of that molecule, so it is still intramolecular. You can also have something called intermolecular bonds, which we'll talk more about later. But those intermolecular bonds exist between two different molecules, not inside of a single molecule. Okay, and lastly, some properties of ionic compounds. Like I already said, they do keep that crystal lattice structure. They tend to have very high melting and boiling points because this intramolecular bond is so strong. And in order to boil this substance, you would have to break that bond, which is very difficult to do. Ionic substances also conduct electricity in solution because of the presence of these positive and negative charges. Anytime you have ions in solution or charged particles in solution, the electricity is able to move between the different ions that are present. And then ionic compounds are also highly soluble, meaning that they dissolve well in water. And this is because if you have a water molecule like we have here, if you remember from Science 10, when we talked about polarity, we talked about the fact that the oxygen end of a water molecule is slightly negative. The hydrogen ends are slightly positive. And that has to do with the fact that the electrons in this bond are not shared equally. They spend more time with the oxygen than with the hydrogen. These are arrows, by the way. And so because of that, this negatively charged ion gets pulled away by the positive end of the water molecule, and this positive ion gets pulled away by the negative end of the water molecule. So because of the polarity of water and the attraction of those poles to the ions in an ionic compound, the ionic compound gets pulled apart and therefore dissolves in the water molecule. And we'll talk more later on about how we determine just how soluble ionic compounds are, because some are more soluble than others, but they are all to some extent soluble. Okay, and I think that is it for today's lesson, but let me know if you do have any more questions.